Hey everyone, hope you're all doing great. As the title says, in this video we are going to cover the most important, difficult and common questions from Chemistry Unit 1, the ones that show up again and again in exams. This is part 2 of a two-part series designed to boost your confidence and exam performance. So without wasting any more time, let's jump straight in. Alright, let's begin with the first question. Four ions are present in a stream of ions in a mass spectrometer. The paths of these ions are shown. So here we go. You got path 1, path 2, path 3, path 4. So now the question is, which of these ions will follow path 1 through the mass spectrometer? Now, if you see something, according to our previous knowledge, that heavier ions will deflect less. Well, this is related to this equation, mass by charge, more popularly known as mass to charge ratio. Now, we all know that heavier ions deflect less, but we can see path 1 is deflecting the most compared to other paths. So, C and D will be out of our option. This leaves us A and B. So, now we know the mass remains constant because obviously 54 is the lowest mass among all of the four options. So, if we tend to make the mass constant, let's say 54, all we need to do is basically check out the charge. Now, if you check out this one, there is +1 and there is 2 plus charge. So if the charge value increases, the mass to charge value in overall decreases. So if the mass to charge ratio value overall decreases, it receives the highest deflection, and vice versa. That means if the charge is low, for example +1, then the mass to charge ratio value will increase, which will result to lower deflection. But since path 1 we can see clearly from our visual diagram that it has been deflected the most relative to its other counterparts, so we can say that B will be the correct answer since it consists of 2 plus charge. Moving on to the next part, naturally occurring chlorine has two isotopes, 35 chlorine and 37 chlorine. Now they said here how many peaks due to the singly charged molecular ions are seen in the mass spectrum of chlorine. Now before that we need to check out the possible combinations of chlorine atoms in chlorine. So there are many possible we can just use these isotopes and tend to find the combination. So one combination such is chlorine 35 chlorine 35, then there is chlorine 37 chlorine 37, and another one involves chlorine 35 chlorine 37. So these are the three combinations. So three combinations basically means three peaks might be present because of three singly charged molecular ions due to the combination of these three. So we can say that is why the answer is 3. The next part says 2-methyl propene reacts with hydrogen bromide to form two possible products. Draw the mechanism for the formation of the major product of the reaction between 2-methyl propene and hydrogen bromide. And they told you to include the curly arrows. So again, in our previous video, we encountered the same type of questions. So in this case, you can clearly see that when the electrophile tends to when the sorry not electrophile when the nucleophile tends to come near the carbon to carbon double bond, so what happens is that the negatively charged carbon to carbon double bond tends to repulse the partially positively charged hydrogen atom in the hydrogen halide nucleophile, which in turn causes the whole bond to break down via a process called homolytic fission. Okay, no, not homolytic. In this case it would be heterolytic fission. The reason why it's heterolytic fission because bromine is more electronegative than hydrogen, and we know how heterolytic fission works. So moving on, the next part is that after the heterolytic fission happens, what happens is that the partially positively charged hydrogen provokes the double bond to break, and in itself it gets added up with any one of the carbon. Okay, so after it gets added up, what happens is that a carbocation is produced. In this case, we will only be showing them, since they said here the major products, we'll only be showing the carbocation which is second degree. There is another carbocation that could be produced, say for instance here, but that would be a primary carbocation. And according to our previous knowledge, we know that this is the trend of stability of carbocations. That means the more stable the carbocation is, the higher the chance it has to become the major product. So in this case, we can see that this if we can produce a secondary carbocation, that means if the carbocation is produced in the second carbon, we can produce a third degree carbocation. And then later on, in the second step, after the intermediate is formed, the bromine tends to attack the carbocation, the positively charged carbocation, and itself gets added to produce the bond. Eventually, we get our halogen alkene right here. So it's very important to see the dipoles, because the dipoles are the first mark that carry. Important to see the second mark where the carbocation will be produced, and also the arrow signs carry the third mark. Finally, the fourth mark would be the correct visualization of the diagram. Moving on, hydrolytic fission produces what? Now, hydrolytic fission, if you check it out right here, there are two types of fission we know that takes place in free radical substitution. One is obviously the homolytic fission, and another one is the heterolytic fission. Now, in homolytic fission, what happens is pretty simple, that two free radicals are produced. But when heterolytic fission takes place, what is heterolytic fission? Heterolytic fission is the process in which any one of the atoms or any one of the element within a bond tends to take the bonded pair of electrons. So in this case, it does not necessarily produces free radicals. What do we mean by free radicals? Species with unpaired electrons. So that's right. So in case of homolytic fission, free radicals are produced. All right, so that would not be our answer. This leaves us C, D, and B. Now, in case of heterolytic fission, free radicals and positive ion is not produced, since obviously if free radicals are produced, then obviously unpaired electrons are present and free radicals are never positive, so that would be out of the equation. And also, if you check out D, since they have also included free radicals, but in heterolytic fission, no free radical is produced. In heterolytic fission, only ions are produced. So in this case, we can say that B is the correct answer. Moving on to the next part, what is the IUPAC name for the compound with the structure shown? Now, if you check it out, you need to check out one thing, that is cis and trans. These are never included in the IUPAC system. So we can easily omit A and B whenever they tell you to write the compound which involves geometric isomerism. E and Z. EZ isomerism is the system which is included in the IUPAC naming system. So in this case, we can automatically omit A and B. Now this leaves us C and D. Now we need to check out the priority groups in both sides. So in this case, it's chlorine. In that case, is obviously methyl group. Now question is, how did we decide the priority group? We decided the priority group based on the molecular masses. We took out the molecular masses of hydrogen and chlorine, and this one and this one. Obviously these two are same, so we can just include it in one of them. Now question is, which one is it, E or is it Z? Since both of them's naming is okay, 2-chlorobutene, 2-chlorobutene. Now we know what? We know that if the priority groups are present on the opposite sides of the carbon to carbon double bond, then it is E. But if if the priority groups of both sides are present on the same side, then we can say it should be Z. So in this case, we can obviously see that both of them are on different sides, so C will be the correct answer. Moving on, describe the formation of the molecular ion of bromine in the mass spectrometer. Include an equation, and they told you not to include the state symbols. So, in the case of a mass spectrometer, when the vaporized sample of bromine is passed through the electron chamber, so an electron gun basically shoots some electrons, which is a beam of high energy electrons is bombarded towards the gaseous bromine molecule via the electron gun, and this is what it happens. Two electrons get knocked out, which results to the production of two bromine 2 plus ions. Now moving on, they have provided you a mass spectrum. You can see, draw the peaks. They told you to basically draw the peaks for the bromine molecular ions, showing the relative peak heights. Now these are the combinations, and based on the combination summation, we can see that the molar masses come at around 158, 162, and 160, because naturally we can find 79 bromine and 81 bromine naturally. Now the abundance may vary, but this is just an molecular ratio we can find if we basically find the ratios of these three by dividing the most smaller number. So That is the abundance, which basically means they're trying to say that bromine bromine 81 is 2 times more in abundant compared to bromine 79. Or you can, other words, you can say bromine, which basically consists of a molar mass 162, is 2 times high in abundance compared to its counterparts. That's right. So again, you just draw 3 straight lines on the molecular masses in the mass to charge ratio. Since obviously the charge remains the same, the mass is changing, so obviously 158, 160 and 162. How we found it out? By checking the combinations. And the combinations they've already provided, they will already provide you the about the types of naturally occurring isotopes that might be present in the nature. All right, the next part, they said the elements carbon and silicon both form dioxides. Carbon dioxide is a simple covalent molecule, but silicon dioxide has a giant covalent structure. So they told you to describe the covalent bond between a silicon atom and an oxygen atom in silicon dioxide in terms of the particle involved. Now we know what? We know that there will be a strong electrostatic force of attraction between the shared pair of electrons and the nuclei of the silicon and the oxygen atom of the bond. Because we know that in silicon dioxide, just like silicon dioxide kind of resembles a giant covalent structure, just like what is present in a diamond structure. So obviously, the shared pair of electrons attraction and the nuclei will provide it the covalent will provide the will result in the formation of the covalent bond produced between them. Moving on, they told you to compare and contrast the covalent bonding in carbon dioxide in silicon dioxide in terms of orbital overlap. Now this is very important. They told you to basically describe in terms of orbital overlap. If you see the similarities, we know what? That in case of silicon dioxide, both basically contain pi bond, or in other words, both in case of silicon dioxide, what I can say is that uh, both contain sigma bond. Why they contain sigma bond? Because obviously sigma bond is common, because there will be a single bond present. And another similarity is that the sigma bond end on overlap is between the atoms. So they're trying to say is that the oxygens do end on overlap, and this results to the production of sigma bond between silicon and oxygen. Now the differences are is that carbon dioxide also contains a pi bond. That's right. The difference is pretty simple. Sorry, 1 minute, I forgot to mention. Sorry, sorry, I think I made a mistake. Actually, silicon dioxide does not contain any pi bond. It just contains a sigma bond. Yes, in case of carbon dioxide, it does, because we get two double bonds between oxygen. So obviously, a sigma pi bond will be present, and we know how pi bonds are produced. Pi bonds are basically produced by the sideways overlap perpendicularly between two carbons, and that too it has to be below the plane of the atoms. They're trying to say if this is the plane of the atom, they are going to be produced below the plane of atoms or above the plane of atoms, whatever you name it. The overlapping will take place above and below the plane. So this is how the pi bond is produced. But in case of silicon dioxide, uh, what happens is then this is the difference between silicon dioxide and carbon dioxide, and only similarity is that in case of carbon dioxide, a sigma bond will also be produced, and obviously here, since there is no pi bond, the single bonds will be by sigma bond, and sigma bond is obviously done by end on overlap between the atoms in this carbon dioxide, and also in in atoms between silicon and oxygen, it is done by end on overlapping. So these are the similarities and differences. Now, the diagram shows the simplified structure of zingiberine, in which part of the molecule is presented by A. Now, they told you to complete the mechanism for the reaction of gingiberine with one molecule of hydrogen bromide. Again, they showed you the gingiberine structure. Now, again, you have to show the electrophilic addition mechanism, where again I showed you countless times previously in this video as well as in the previous video, that at first the electrophile, what's going to happen as it approaches near the carbon to carbon double bond, what's going to happen is that it's going to attract the negatively charged double bond is basically going to provoke the partially positively charged hydrogen atom in order to break down by hydrolytic fission, and then the carbocation gets formed, while the bromide ion basically attacks the intermediate carbocation, and at last the product is produced. As I mentioned a little while back, the 4 marks get involved with the correct alignment of the arrows, the correct position of the carbocation, and of course the correct visualization of the correct product being produced. Now they say a drop of an aqueous solution of green copper to chromate is placed in the center of a strip of damp filter paper. Now, the ends of the filter paper are connected to a DC power supply, they say. Now, what will be observed after a few minutes? Now, you need to understand thing. If I talk about copper to chromate 6, in case of copper to chromate 6, we have Cu2 plus and CrO4 2 minus. So what happens? This is obviously blue in color, and that would obviously go towards the negative electrode, and this is yellow in colors, that would obviously move towards the positive electrode. So as we can see clearly, yellow color has moved to the positive, and while blue color moves to the negative end, because we know the colors of these respective individual ions. That is why C is the correct answer. Now they said here, which of these isoelectronic ions has the smallest ionic radius? Isoelectronic basically means all of them have the same number of electrons, regardless of whether it's a cation or an anion, they say. Now, always remember one thing, that the ionic radii increases with increasing negative charge, and also remember another thing, that ionic radius decreases with increasing positive charge. Because obviously if you increase the positive charge, that means if the proton number basically increases or the nuclear charge increases, obviously the electrostatic force of attraction between the outermost shell and the nucleus will increase. That would result the decrease in ionic radius, and vice versa with increasing negative charge, considering the repulsion increases. Now we can clearly see that aluminium has the most number of protons, so that kind of aligns with our second statement. So obviously aluminium, among all of its counterparts, will be the one which has the smallest ionic radius. Now the next part is that which properties of a cation result in the greatest polarizing power. Now according to Fajan's rule, what do we know about Fajan's rule? We know about Fajan's rule is that smaller radius and larger charge of cation results to greater polarizing power, and that is kind of correct, because if you check out the formula, charge by r squared is the charge density formula. So with a smaller radius and with a higher charge, our the polarizing power or the charge density basically increases. So if the charge density increases, in turn the polarizing power of that specific cation also increases. That is why the answer would be D. Now again, let's move on to the next one. The question is about alkenes. Alkenes contain a carbon to carbon double bond that consists of a sigma bond and a pi bond. Now they told you to complete the diagram to show the areas of electron density for each bond and label the sigma and the pi bond. So if you check out right here, then we can clearly see that the pi bonds basically is produced, we know a little while back as well, we talked about that the pi bond is produced by the sideways overlap of p orbitals, and that too perpendicularly above and below the plane of the carbon to carbon double bond. While in the carbon to carbon double bond, we know in a double bond a pi bond is there, and along with that a must sigma bond should also be there. So obviously we need to show the sigma bond, and we know sigma bond is produced by a sideways end-on overlap of p orbital between two carbon atoms. So that is how you draw the diagram of it and show the electron density map. Now, propene we know is an alkene. The reagents needed for 3 reactions of propene, you can see, is shown. Now, what will happen when you basically react these 3 types of reagent, and these type of questions are very important for organic synthesis in chemistry unit 1. So this is high time that you focus on the organic synthesis. Uh, so in case of acid and steam catalyst, what happens that an alcohol is produced, as obviously the carbon to carbon double bond breaks down and OH is taken out from the steam and it joins there. On the other hand, acid by potassium manganate 6 acts as an a stronger oxidizing agent, and this results to the production of a diol, and here an alcohol. And always remember, with bromine it's going to be an addition reaction which results to the production of a dihalogenol alkane. Okay, moving on. Propene also reacts with hydrogen bromide. Give the mechanism for the reaction to form the major. Again, the same concept of the mechanism. All you do is show the proper 3-way of the electrophilic addition mechanism, just as I have countlessly talked about a lot of times in the previous video as well as the start of the video in various questions. So you can check it out again like this, and then let's move on to the next one. Now this question is about the bonding in the elements of period 3 of the periodic table. Now the melting temperatures of the period 3 elements are shown on the table, and now they told you what is meant by the metallic bonding. Now if I say so, the metallic bonding is what? It is basically the electrostatic attraction between the positive metal ions and the delocalized electrons. That's right. Whenever what is metallic bonding, whenever we basically talk about metallic bonding in metals, what happens is that positively charged ions are metallic ions are produced with the electrons coming out to get delocalized, and the attraction which is produced between these electrons and the positively charged ions, that attraction is very strong, which is known as metallic bonding. Next part, they said melting temperature depends on the strength of the metallic bonding. Now explain how it makes magnesium more stronger than sodium. Like I said, since positively charged ions are produced, so one thing for sure, it depends on the charge of the ion, and it also depends on the ionic radius of the ion. So obviously Mg2 plus is a higher charge, so the electrostatic force of attraction between the delocalized electrons, between two delocalized electrons and 2 plus charged ions would far be greater than one electron and a 1 plus charged ion in sodium. So obviously that's one reason. Another reason is that since Mg2 plus is a greater nuclear charge, so obviously this ionic radius will be smaller than Na plus. So obviously Mg2 plus will have a greater charge density than Na plus, since a lot of since it has more nuclear charge and more electrons, so obviously the number of electrons will be higher, so that is why the charge density will all be higher than Na plus. So due to the greater charge density, obviously this will lead to a greater attraction as well, contribute to the greater attraction between Mg2 plus and the delocalized electrons due to the greater density. So these are basically the two factors which play down here that make magnesium much more stronger than sodium. Moving on to the next part. This question is about the ionization energies of the elements in period 2 of the periodic table. So these are the first ionization energies we can see of period 2 elements. Now give an equation that represents the first ionization energy of lithium, and they told you to include the state symbols. Well, this is pretty simple. We know in ionization energy, one electron basically gets given out and all of them stay at their gaseous state. Moving on, explain why there is a general increase in the first ionization energy. Now we know what happens across the period. We know that the nuclear charge increases as the number of proton increases. That's right. Now the one thing that happens is that as the number of protons increases, it also causes the atomic radius to decrease. Why is that the case? Because if the nuclear charge increases, the attraction between the outermost electrons and the protons in the nucleus will become stronger. So that is why the atomic radius will decrease. Now there is another thing that happens, that is the electrons in the same quantum shell are get removed. So the outermost electrons will more or less will experience the similar shading. That's right. Since all of the elements are present, since all of the elements are present in the same period, the number of electron quantum shells are not increasing, which means the outermost electron is being removed from the same shell. So that means the number of inner shells are not increasing or decreasing. So that means the shielding effect tends to remain the same. So the only factor that is working down here is the increasing nuclear charge factor. So force of attraction increases. So that is why the ionization energy is a increasing ionization energy is a general trend across period from left to right. Now obviously we know there are some anomalies in chemistry, so this is no exception. Look, explain why the first ionization energy of oxygen is lower than that of nitrogen. Now if you talk about between oxygen and nitrogen, you need to check out the electronic configuration and analyze both of them. Look, even though oxygen has one more proton than nitrogen, we need to see that the electron which is basically removed is being removed from a full 2p orbital that is paired, while in nitrogen it is from a singly occupied 2p orbital. Now we know that nitrogen is 7 while for oxygen it is 8. So if you now basically draw, it is going to be 1s2 2s2 2p3. So in case if in case of nitrogen, if we check out the p orbitals, So all of them are basically, they occupy the 2p orbital in single format. They are not in paired format. But in case of oxygen, what happens is that there are 8 electrons, so one extra electron is there. That means one of the electron is at its paired state. So that's one thing. So more energy is required to remove it. Now we know another thing, that more energy is required to remove an unpaired electron, and this is a proven fact, than a paired electron. So obviously what is happening is that nitrogens, in the case of nitrogen, the outermost electrons are in their unpaired state in the 2p orbital. So this is the most stable form of any electronic configuration. That is right. In case, whenever the electrons are in their unpaired state and they fill up all the orbitals in a subshell, in a specific subshell, they are considered to be at their most stable state. And anything to, if you want to remove something from their stable state, we require a huge amount of energy. So if you now compare it, we can clearly see that the nitrogen's electronic configuration is more stable, and making it more unfavorable to remove an electron with lower energy. So more energy is required. So that is why the reason why oxygen has a lower first transition energy than nitrogen is due to its stability. All right, let's move on to the next one. All the successive ionization energies of nitrogen are shown on the table. Now the table is provided, we can see that clearly. Now the question here is that, uh, explain the trend. Now we can clearly see what is happening. The trend is tend to increase, is increasing. Now if we check out, why is the general trend increasing? Well, it is increasing because as the electrons are getting closer to the nucleus while having the same positive charge, which means the electrons are more strongly attracted to the nucleus. So at first, the first electron gets removed from the outermost shell, and these electrons are getting removed from the second quantum shell, while these are basically getting removed from the second quantum shell, and while the last two are getting removed from the first one. So we can clearly see a change, a big change here. So how will we understand that? How we understand, so which electron are removed from which shell? If we check out the big change down here, we see a big jump from 14028 to 2856, and then from here we see that we see a big change down here, that we see 4 electrons are being removed, and then we have these 2 electrons being removed from the last shell. Now if you check out down here, there is a big jump between the third and fourth ionization energy, as the fourth electron is being removed from the new subshell. So you can clearly see that, what we can clearly see that after the 3 electrons get removed from the 2p subshell, basically if they're removed from the 2p subshell as stated above down here, we see a big jump. We see about a big jump, about 5 6 7 3,000 something jump, and in terms of when we find the difference, this basically means that the fourth electron is being removed from a new subshell, which is obviously the 2s subshell. And now obviously 2s has 2 electrons in nitrogen, so these are the electrons which are removed from the 2s subshell. And again we see a big jump, so these are removed from the 1s subshell, since obviously there's a big jump between 5th and 6th, and as the 6th electron is removed from a new quantum shell. So we need to write all of this down and by analyzing the data. And obviously why it is increasing, because as we keep on removing the electrons from the subshell, what is happening is that the electrons which are present in the 2s and 1s, they're more closer to the nucleus. So the factor, since they're more closer to the nucleus, obviously their force of attraction will be higher, and that is why more heat energy will be required to overcome these forces, and in turn ionization energy increases. Moving on, in which series are the ions in order of decreasing ionic radius? Alright guys, I hope everything's been clear so far. If you're enjoying this and want to practice more papers or complete the syllabus with me before your exam, here's something for you. At Exam Essentials, we offer 2 signature courses before every session. The Question Papers Marathon course, perfect if your exam is within 2 months. And of course, the another one, the High Impact Crash Course, which is ideal for those with 3 to 6 plus months to go, focused on full concept coverage and strategy. Course details are in the description. You can also message us directly via WhatsApp at the number below, or reach out on our Facebook page, Exam Essentials. Let's make your preparation stronger, smarter. So if you check out the ions present down here, so we can clearly see that one thing's for sure, that cations will always be almost always be smaller than anions, because obviously they lose electrons compared to anions which gain. So obviously that in that sense we can say that since they lose electrons, the force of attraction between the remaining electrons will increase between the nucleus. So in this case we can easily omit A and B from our options. So this leaves us C and D. Now obviously if you compare the anions down here, we can clearly see that among, if you compare nitrogen and oxygen, or even with sulfur, we can see that nitrogen loses the most number of electrons. So obviously what is going to happen, since it loses the most, since it basically, sorry, it gains the most number of electrons since it's an anion, so obviously the repulsion will be greatest down here. So this will have the largest ionic radius, and then secondly the O2 minus will be, and at last the fluoride ion will have the low, lowest ionic radius among these three anions. So we can say that C will be our correct answer. Another thing, that a stable ion contains 18 electrons, that's right, M3 plus, and they have provided you these options, like in which block of the periodic table is element M found. Now it says that it found 18 electrons, all right, and they said here 3 plus. So obviously this basically means what? That means it basically lost 3 electrons, M3 plus, but before it was M, it basically lost 3 electrons to produce 3 plus. So what will be the actual number of electrons? The actual number of electrons would be 18 plus 3, that would be 21 electrons. Now 21 electrons, if you basically check out the periodic table, you will notice that 21 electrons basically corresponds to element M. The element M is basically scandium, which is obviously a d block element. Why it is a d block element? Because its outermost electron is present in a d subshell, so obviously we can say it's a d block element. Moving on, if you check out in which series are the elements in order of increasing melting temperature. So if you check it out down here, if you check out for group 1, the melting point we know decreases down the group. We need to know some facts. For group 7, we know melting point increases down the group. So if that's the case, though, we can clearly see that they're showing that it is moving above the group. So obviously this is not the correct answer. So if we move on, the next one, melting point decreases down the group. So obviously if you they basically showed this one, they basically showed you period wise of from the lithium group, from the lithium period, and this one she showed you group wise. So obviously what happens is that since uh, if you go down the group, it decreases, but they told you increasing melting temperature, so C is not going to be the correct answer, as well as A. And if you talk about B and D, you have to check out that carbon has the highest melting point in period 2. You have to remember this, means they both provided B and D in the period format. So carbon has the highest melting point in period 2, and you have to remember silicon has the highest melting point in period 3. So if that's the case, so obviously silicon should be there. So that's not the correct answer, which leaves us B as the correct answer, because obviously carbon has the highest melting point in period 2, and then this is the most viable option. The next part is that in solid state, beryllium chloride forms a polymeric structure. So this is the diagram they show. The diagram uses lines and arrows to represent the two different types of covalent bond. They told you to describe how each type of bond is formed. Now remember one thing, the covalent bond, we need to say one thing, that is how the dative covalent bond is produced. That is what they basically told you. Now if you check out the arrow down here, what does it represent? The covalent bond represented by the arrow is formed when one lone pair of electrons is donated from one atom. So that's right, the chlorine basically donates one of its lone pair of electrons to an empty orbital of beryllium, considering it has 3 bond pairs and 1 empty orbital. So obviously the lone pair has got a chance to, that is why the chlorine basically donates a lone pair, so we can occupy the empty orbital of beryllium and produce the dative covalent bond. And if I talk about the linear signs with no arrows, these are basically normal covalent bonds which are produced through bond pairs between chlorine and beryllium. Now explain why gaseous beryllium chloride and solid calcium chloride have different types of bonding. So if I talk about this, that first of all you need to see that beryllium is more electronegative to calcium. All right, this is the first thing you need to understand. Since the the negativity is higher, so obviously the difference in electronegativity between Ca and Cl will obviously be greater than Be and Cl, right? So if that's the case, obviously we know that if the difference of electronegativity is high, the covalent characteristics in a compound or a bond is much more higher. So we can say the BeCl bond will have a higher degree of covalency. uh, we can say it will have a higher degree of covalency, since the difference is very low in BeCl compared to CaCl. So if the difference is low, so obviously this will have a higher degree of covalency compared to CaCl, which will have a higher degree of ionic character compared to covalency. So this is the reason. So yeah, that is what I have written here. You can see. So that would be the reason why beryllium chloride and solid calcium chloride have different types of bonding. You can also talk about in polarization format is that, like for instance, beryllium is smaller than calcium, so obviously it will have a greater charge density, and we know that with a greater charge density makes the cation more have a higher polarizing power compared to Ca2 plus, which will have obviously a lower charge density, considering it has a lower, so obviously it will have a lower polarizing power. So due to the higher polarizing power, BeCl bond will have a higher degree of covalency. So the degree of covalency can either be described in two ways. You can basically talk about in terms of electronegativity difference, or you can talk in terms of polarization or polarizing power, and compare it. Moving on, they said here the graph shows the first ionization energies for the elements in period 3. Now they told you to explain the general increase in the first ionization energy from sodium to argon. Now again, a little while back we discussed this type of question little while back. So again, the same answers would be the nuclear charge increases, the number of proton we know in the nucleus increases, and then the additional electrons are in this. Now another thing that you need to remember, since obviously all of them are in the same period, so obviously the additional electrons which are present in the same shell, because the number of quantum shells are not increasing. So each electron being removed from each element will experience the same shielding, considering the number of inner shells remains the same. So that would be the answer of for the general increase. Now again, now they told you during the previous question, in a previous question a little while back, we saw they told you to explain the anomalies between ionization energy between nitrogen and oxygen. In this case, they told you to explain the anomaly between magnesium and aluminum. Now if you talk about magnesium and aluminum, you need to see that the first electron is removed from a 3p orbital in aluminum, while in magnesium it is removed from a 3s. So that means the p electrons are shielded by the s electrons, so obviously they will require less energy. We know that if the shielding is higher, energy will be less, because due to the shielding, the force of electrostatic attraction between the nucleus and the outermost electrode tends to decrease. So that is why the reason is that aluminium will tend to, the electron, the first electron to be removed from the aluminium will require less energy compared to magnesium. Now, alkanes and alkenes are obtained from crude oil. Now, you have to describe how a sample of octadecane can be obtained from a mixture of alkanes. So, there are many ways you can do it. The first things first you have to do is that you need to vaporize the mixture and pass it through a fractionating column. And we know the fractionating column tends to contain a temperature gradient with 400 degrees Celsius at the bottom while 40 degrees Celsius at the top. So the fractions are going to condense at different heights according to their boiling temperature. In fractions, we basically mean the different chains of hydrocarbons which are present in the crude oil. And obviously, due to this temperature gradient, the column will be hotter at the bottom and cooler at the top. Now, they said here, suggest an explanation for the decrease in atomic radius as atomic number increases down across a period. Again, a little while back, we saw the same type of, it basically relates to the previous question down here. It's just that you need to explain it a little more briefly. Uh, just 3 marks. So again, as the atomic number increases, again you need to talk about the number of protons in the nucleus also increases, which means the outer electrons are more strongly attracted to the nucleus. And then again, now one thing's for sure that you need to see is that you need to now analyze all the factors and then conclude with the last factor. So this is one factor, number of protons are increasing, so obviously the force of attraction will increase. Now there is another thing, that is since the number of protons are increasing, the number of electrons are also increasing. That means the electron-electron repulsion, or in other words, the shielding effect, is also increasing in the outer shell. Now, what's going to happen is that the increasing nuclear charge is going to partially offset, or basically overcome, the factor of the increased electron repulsion. So and that's one thing. And since if I talk about another thing, that since all of the electrons are being removed from the same quantum shell, fairly the shielding will remain constant. So the only factor which is causing the decreasing the atomic radius, actually is basically the increasing the number of protons. So that is the reason why the force of attraction increases and the atomic radius decreases as the atomic number increases across a period. Now, solid phosphorus 5 chloride contains PCl4 plus ions. So they told you to draw a dot and cross diagram. Now we know this is a covalent uh, bond. So obviously phosphorus will produce 3 bond pairs with chlorine and so on and so forth. And since it's charged, so we need to include a charge with a bracket. It contains 1 extra electron less. Now, if I talk about the shape of the PCl4 minus, so obviously since there are four chloride atoms, so obviously it will be a tetrahedral shape, just like a diamond shape. And the justification is that since there are 4 bond pairs and no lone pairs around P, the electron pairs are going to arrange themselves into a position of minimum repulsion, maximum separation. This is very important to write in this type of questions where they ask you for justification. And this basically comes from the VSPER theory, which is basically the valence shell electron pair repulsion theory. Okay, now the next question, they say, is the period 2 element with the highest melting temperature. Obviously it's going to be carbon, because carbon is the first element in period 2 and then it moves on. So obviously carbon will be the one highest melting temperature. Then again, which of these is the greatest electrical conductivity? Now if you analyze all of the 4 molecules down here, pure water doesn't conduct as it has no ions, but if it is aqueous format, then water will be. So water is out of the equation. SF6 is basically a simple, has a simple molecular structure, so it does not contain any charged molecules or ions, so we can say that it does not basically conduct any electricity. That's out of the equation. This leaves us 8G and Na2O. Now we know this is an ionic compound, but since ionic compounds do not conduct at their solid states, the only option here is 8G. C. Moving on, the next part, this is which of these ions has the greatest ionic radius. Now a little while back we saw that the same type of question they have provided in January, in 2022 June unit 1. A little while back we saw previously that in that case they told you to find the lowest ionic radius, but now they told you to find the greatest ionic radius, and all of them are isoelectronic. So in this case obviously the answer would be A. It's just the reverse. A little while back we give the answer D because they told you to find the lowest ionic radius. In this case it will be the greatest ionic radius will be obviously nitrogen, because it has gained the highest number of, it has gained 3 extra electrons, while it also contains the least number of protons. So obviously the force of attraction will decrease due to the increased repulsion of the gained 3 extra electrons. Now if you check out which of these ions is the greatest polarizing power, so again in this case we can see that we have uh, 4 cations present. So obviously the one which has the highest charge will have the greatest polarizing power according to Faddan's rule, because it is also a little while back I showed you that charge by r square. So if charge increases, the whole charge density increases, which results to a greater polarizing power. Moving on, which of these does not have a structure formed by a giant lattice of carbon atoms? Diamond does, graphene does, graphite does, but C60 fluorine doesn't, because it's the only compound which has a simple molecular structure. If I talk about which of these molecules is the most polar, you need to check out which one has the highest electronegativity difference. Now, without any doubt, hydrogen has the lowest electronegativity and fluorine has the highest electronegativity in the whole periodic table. So obviously the electronegativity difference will be highest between HF compared to all other bonds. So obviously A will be the correct answer. Explain why the first ionization energy of sulfur is less than the first ionization energy of both phosphorus and chlorine. Now if I talk about this, uh, if you check about sulfur and phosphorus chlorine, if you check out the electronic configuration, the outermost electrons are removed, are in the 3p subshell, which means the outermost electron experiences a fairly constant shielding in all 3 elements. That's right. In case of phosphorus, in case of chlorine, in case of sulfur, all of the outer electrons are present in the 3p subshell. It's just that the number of electron is different and nothing else. Now, the only problem is that chlorine has the most number of protons. So obviously, the outermost electron will be more strongly attracted to the nucleus, so more energy is needed to remove it. So that's right. Compared to the three elements, even though all of the outermost electrons are present in the 3p subshell, that means they will experience the same amount of shielding. But since chlorine has the greatest nuclear charge, due to the great most number of protons being present, it will experience the outermost electron present in the 3p subshell will experience the greatest force of attraction towards the nucleus. So obviously, in order to overcome it, more heat energy is required. Now, in case of phosphorus, the electron is removed from a singly occupied 3 orbital which is unpaired. So more energy is required to remove an unpaired electron than a paired electron like in sulfur. That's right. In case of sulfur and case of phosphorus, if I say so, in phosphorus we know that the outermost electrons are basically arranged in something like this 3p3. All of them are in their unpaired state, but in case of sulfur, since there are 4 electrons in the p subshell, one of the electron is in its paired state. Now, I told you a little while back, if the electrons are present in their in their unpaired state, they are in their most stable state compared to the 3p4 where where they're in their unstable state. If one of the electron is in pair state, the whole structure becomes unstable. So obviously, if you want to remove an electron from its most stable state, you require more energy compared to the one where you tend to remove it from its unstable state. So obviously, that is the reason why phosphorus tends to have and due to the presence of two electrons in their paired state, more repulsion is experienced. To be honest, the repulsion basically increases the unstability, and here, since there is no repulsion due to their unpaired state, the stability is higher. So basically, due to the difference in the stability, the the energy required to remove an 3p orbital in phosphorus is obviously more compared to the one which is in from sorry from sulfur, from phosphorus is more compared to sulfur. All right. A sample of sulfur contains 4 isotopes. So state what is meant by the term isotopes in term of subatomic particles. Now we know what are isotopes. Isotopes are basically atoms of the same element with same number of protons but have different number of neutrons. This is something we have learned from our IGCSE level. So I don't think there's that much to understand. It's very simple. The question here is about the structure and bonding of group 5 chlorides. They told you the nitrogen trichloride has a molecular structure, we can see that, and this is the displayed formula of a molecule of NCl3. Told you to complete the table for this molecule. Now if I check it out, the number of bond pairs around the nitrogen atom, we have 1 2 3 bond pairs, and we know that nitrogen tends to have a one lone pair, so that would be one lone pair. And now we know that 3 bond pair and 1 lone pair combination tends to provide a trigonal pyramidal, which obviously has a 107-degree angle. So this is the answer. Again, they said under standard conditions, phosphorus 5 chloride is a solid made up of PCl4 plus cations and PCl6 anions. So they told you antimony chloride is a liquid made up of SbCl5 molecules. They said here why PCl5 has a higher melting temperature than SbCl5. Now you need to check out the structures here. Well, PCl5 is a giant ionic structure, right? So if it is a giant ionic structure, automatically has a strong electrostatic force of attractions between the PCl4 and PCl6 minus ions. So due to the strong force of attraction, a huge amount of heat energy will be required. But in case of SbCl5, obviously SbCl5 is a simple molecular structure, so it only tends to contain weak intermolecular forces between its molecules. So that, and if it's weak, so little energy would be required to overcome it. So this is the reason why PCl5 has a comparatively very large high melting temperature compared to SbCl5. Now at low temperatures, they say the same question, SbCl5 converts to Sb2Cl10, which contains dative covalent bond. Now we know what is a dative covalent bond. It is basically a type of covalent bond which is formed, or it's a type of specialized covalent bond which is formed when an empty orbital of one atom overlaps with an orbital consisting of a lone pair of electrons from another atom. We saw a little while back how beryllium and chlorine accommodates, where chlorine basically donates one of its lone pair to a empty orbital of beryllium structure. So that's how dative covalent bonds are produced. Moving on, state one similarity and one difference that would be seen when propene is mixed with separate samples of acidified potassium manganate 6 solution and of bromine water. Now, if I say so, one thing that you need to see the similarity, that it's both would show a color change to colorless, because obviously both of them are going to get decolorized because oxidation takes place in both cases. Now, what's going to happen in case of bromine water is that the color would change from orange to colorless, while color would basically change from purple to colorless with acidified KMnO4 solution, because obviously KMnO4 and potassium manganate 6, because obviously in with bromine water we know what happens is that the orange color of bromine water becomes colorless, and the KMnO4 potassium manganate 6, the purple color of KMnO4 becomes colorless. That is the reason the color changes are different, but in both cases it will become colorless because oxidation takes place. Moving on, the same type of question we have experienced countless times before. Propene reacts with bromine monochloride BrCl to form 1-bromo-2-chloropropene as the major product. Now they told you to complete the diagram bromine monochloride to show the dipole. So as you can clearly see, this is basically the dipole, where in a dipole we tend to basically show the partially positively charged and the partially negatively charged atom. So that's how you basically show, and this is the partial charge sign. They again told you to draw the mechanism, and this mechanism is obviously electrophilic addition, and we know what happens in electrophilic addition. We have explained it countless times, where heterolytic fission again breaks down due to the provocation of the double bond, and again carbocation gets produced in the secondary carbocation, since it's more stable than 1 degree carbocation, and it will produce a major product. So obviously the chloride ion basically reacts with the carbocation to produce the final product. And we know the 3 marks are there for the correct alignment of the arrows, for the correct attacking of the chloride ion towards the carbocation, and the correct position of the carbocation, and also as well the correct visualization of the correct product. Moving on, the E isomer of beta farnesene can also be obtained from one starch. Now explain why beta farnesene exhibits geometric isomerism and has only 2 geometric isomers. You may label the structure and use this in your answer. Now if you check out right here, if you check out on these two parts, see there are 2 different groups on each carbon of the carbon to carbon double bond in the middle. So as you can see clearly, these are the 2 carbons where you see this is one different, and that is one, and in this carbon this is one different group attached. So the first condition for geometric isomerism to happen is that 2 different groups must be attached with the carbons present in the carbon to carbon double bond, and due to the presence of the double bond there is restricted rotation. That's the second condition that has come up. So due to these 2 conditions being present already in this structure, we can say this structure exhibits geometric isomerism. Moving on, the compound alpha farnesene C15H24 is a structural isomer of beta farnesene. Again, this will talk to you about what we meant by the term structural isomer. Well, structural isomers basically have the same molecular formula but different structural formula. This is very easy. That means they tend to have the same molecular formula, it's just that the structural formula will change, nothing else. Maybe the CH2 might come there and the CH3 might go there. That's it. Moving on, they said the mass spectrum of a sample of an element is shown. As you can see clearly, they told you what is the relative molecular mass of this element. Now, in order to find the relative molecular mass, it is pretty simple. All you need to do is basically just check out the table down here. So we can clearly see that 63 and 65, these are the 2 molecular ion peaks. You basically multiply it with their relative abundances. So one is obviously we can see is about, we can clearly see the we basically multiply the relative abundances according to their relative abundances, and then we find it out. So one is obviously 46%, we can see, and another is about 20%. This is about 20%, and another is about 46%. So we basically multiply their respective relative abundance with the corresponding molecular ion peaks, and then you basically divide it with the total abundance in order to get the relative atomic mass. So that's how you get it, about 63.6 ton, which is C. Moving on, which pair of ions will form the compound with the most covalent character? Again, in order to judge the covalent character, we need to check out the electronegativity differences. Now, if you check out all of them down here, we need to know one thing, that electronegativity increases across a period and decreases down a group. That means the least electronegativity difference will be between Li plus and I minus, considering Li is present. Li is the element above all other elements down here, which is the topmost element in when it comes in the group. While if I talk about I minus, it is present. It is the most downmost element when it comes in terms of the in term when we turn to judge in terms of group in the periodic table. So obviously we can say, since this basically has obviously this has the highest electronegativity and this has the lowest electronegativity, so obviously the difference will be the highest. So obviously if the difference is the highest, covalency degree will be the highest, so obviously A is the correct answer compared to other counterparts. Now this question is about the structure of atoms. They told you what is meant by the term orbital. Well, we know what is an orbital. It is basically a region within an atom that can hold up to two electrons with opposite spin, and we know why, because of Pauli exclusion principle. Or you can say it is a region which has 90%, there is 99% probability of two electrons to be present with opposite spins. Again, state the shape of an s orbital and the shape of a p orbital. Again, s orbital is spherical and p orbital is dumbbell shaped, we know that, like this. Again, describe what can be deduced about the electronic structure of sodium from its successive ionization energies. Well, if we check out the electronic configuration, it is 281. Now obviously what's going to happen, it is going to be 1s2, 2s2, 2p6, 2p4 to be exact. So what's going to happen is that there's going to be a big jump in ionization, between ionization energy 1 and 2 and between 9 and 10. Well, why 9 and 10? Because obviously there's being a shift from p to s. So again, you're going to see a big change in the first and the second, considering the both of them are being removed from the first quantum shell. So we can say it can be deduced that there are three quantum shells, because obviously there'll be there's going to be two jumps. So two jumps basically means there are three quantum shells. So it has one electron in its outermost shell and eight electrons in its second quantum shell. That's right. For if I talk about the thing in this case, so obviously in the outermost shell it has only one. If you talk about in this way or that way, it's the same thing. So since it has one electron in its outermost shell and eight electrons in its second quantum shell, we can say these are more closer to the nucleus compared to the two electrons. So obviously if they're more closer to the nucleus, more heat energy will be required compared to the one electron which is removed from the outermost electrons. This is the reason why sodium this I mean, by judging from the electronic configuration of sodium, we can basically deduce the successive ionization energies of it. All right, next, draw a dot and cross diagram of the ammonium ion. Now since it's an ion, obviously there will be a charge, so you basically do the bracket, and obviously since it's a positive, it's going to be we know that NH4 plus, so it's going to be a positively charged ion. So obviously you're going to and because obviously it contains one less electrons, that is why there's going to be a positive charge down there. So this is the answer. Now again, explain the shape of the ammonium ion using electron pair repulsion theory. Now it will have a tetrahedral shape because there are four bonding pairs of electrons which arrange themselves into a position of maximum separation, minimum repulsion. A little while back we saw a justification question previously in the video. So whenever you try to write the electron pair repulsion theory, always try to basically add these two words, maximum separation and minimum repulsion, because these are the two mark scheme points which are always present and are consistent with in each year. We saw it in 2021, we also saw in 2022, and we are also seeing in 2020. So these are some things which you need to check out while if you want to basically utilize your marks during the main exam. State what is meant by the term biodegradable. Well, biodegradable basically means which can be broken down by microorganisms, something which can be broken down by microorganisms, that is known as biodegradable. Now, what are the three advantages of biodegradable polymers? Now, they take less time to break down than most plastics, and when they do break down, they break down into non-harmful products. That's right. They reduce waste going to landfills. They do not require incineration. They come from renewable resources. Obviously, they come from renewable resources because otherwise they cannot be biodegradable. They come from organic matter. And the use of biodegradable polymers reduce pollution. since they can be recycled, so obviously they reduce the chance of pollution. And they cannot break, another thing is that they basically break down into non-harmful products, unlike some products which break down to produce greenhouse gases. So obviously they contribute very less to pollution. So biodegradable polymers, these are the three advantages. Now isoprene is used to make synthetic rubber. The skeletal formula of isoprene here is shown, and state isoprene, why isoprene does not have a geometric isomer. Now if you check out the double bonds here, both double bonds in isoprene have two atoms of hydrogen on one end. But a little while ago we told you, for geometric isomerism to happen, we require what? We tend to require two different groups attached to the carbons present in the double bond. And another thing that you need to see is that even though the double bond is there, but two different groups are not attached. We can see in one of the carbon two hydrogen atoms are attached. So obviously we can say that these won't show geometric isomerism regardless of whether they have double bond or restricted rotation, because for geometric isomerism to happen, you require two different groups being attached to two of the carbons in carbon to carbon double bond. Now, moving on to the next question, give a reason why double bond may result in geometric isomerism. Now, obviously, there is restricted rotation about carbon to carbon double bond. So, obviously, this is one reason why double bond may give you a geometric isomerism. Like the plane in where the, the plane where basically the is present, this cannot basically rotate clockwise or anti-clockwise, plane where the double bond is present. So due to this restricted rotation, we can basically it may result to a geometric isomerism between the different groups which are attached to carbon. Now, which of these ionic compounds will be expected to have the highest melting temperature? Now, before that, we need to check out the which one has the greatest charge in the smallest ionic radius. So obviously among all of them, we can say that among Cl and F, obviously these two are not out of the option, which leaves us this one and this one down here. So we can say that both of them have great charge. The anions have great charge and the cations have great charge. So if you compare B and D, we need to check out which one has the smallest ionic radius. So if that's the case, obviously smallest ionic radius will be magnesium, considering it has considering it is be above calcium. So obviously it has a higher nuclear charge compared to uh, calcium, so obviously it will have a smaller ionic radius. So that is the reason why it will have the highest melting temperature. All right, moving on to the next part, which of these compounds is the greatest covalent character? So if you check out A, B and C, D down here, we need to check out the electronegativity difference again. Now the one with the the, which has basically the least electronegativity difference, obviously it will have the greatest covalent character, and vice versa. That means if there is electronegativity difference is higher, there's higher chance it will have ionic character. Again, we can see that among the, we know, among, if you compare magnesium and beryllium, obviously magnesium has a higher electronegativity compared to barium. So obviously barium is out of the equation. Now again, if I talk about fluorine and iodine, again fluorine has the highest electronegativity value, and compared to iodine obviously it is highest. So obviously the electronegativity difference between magnesium and iodine, because magnesium as the highest here and iodine as an anion has the lowest. So obviously highest minus lowest will have the least covalent electronegativity difference. So the least covalence, this mgi2 will provide the least electronegativity difference. So obviously the degree of covalency character will be greater in mgi2. So B is the correct answer. Moving on, explain the difference in the first ionization energies of chlorine and bromine. We know that bromine has lower first ionization energy than chlorine. Now we know that why, because as the first ionization, because we know that as we go down the group, the first ionization decreases. Why? Because as we go down the group, even though the nuclear charge increases, that's right, that like if the see, even though the atomic number increases, that means in turn nuclear charge increases, what happens is that a new quantum shell is added on each equation. So in the addition of new quantum shell basically means that the atomic radius increases, right? So if the atomic radius increases, the energy required to remove the outer electron will be higher. because obviously no, the energy of the outer electron becomes higher. So one things that happen is that due to a new shell being added, the what happens is that the nucleus the ionic radius tends to increase. That's one thing. And the secondly, that what happens is due to the addition of one electron one electron shell along with more electrons, what happens is that there is increased shielding because from the inner electron, because the number of inner electrons and the number of inner shells are increases. So that is why there is increased shielding. Now due to the effect of the new shell and the increased shielding, these two factors basically overcome the effect of the increasing nuclear charge. Like I said a little while back, that even though the proton number increases, or even that means even though the nuclear charge increases, these two factors are much more in priority taken compared to the nuclear charge increasing priority. The reason why the ionization energy tends to decrease as we go down across groups. Again, one hazard symbol for 1,2-dichloroethane is shown. By identifying this hazard, give one way of minimizing the risk when working with 1,2-dichloroethane. Now, this hazard symbol obviously means that the substance 1,2-dichloroethane is flammable. So obviously that means that if you bring 1,2-dichloroethane near the fire, it may it may cause explosion. So by catching fire. So that is why to avoid this risk or minimize this risk, the student should avoid naked flames near it. Basically meaning they should not keep any source which provides fire or flames near 1,2-dichloroethane. And for that they can use electric water bath to heat, so this will greatly reduce the risk. Or they can heat it in an inert atmosphere, or you can only use small amounts of it. So in that case, if small amounts are used, then there is very less chance of getting it of catching it into fire. Again, there are two reactions of cyclohexene shown. You can see they told you to classify the type of reaction occurring in reaction 1 and reaction 2. So in reaction 1, what is happening in reaction 1 is that hydrogenation is taking place, where you can see the double bond breaks down in which results to the addition of hydrogen. So obviously it's addition reaction. Hydrogenation is much more a professional way of saying it. And for reaction 2, if we say so, we can see that alcohol is being added. A little while back we saw in a previous question that in order to produce an alcohol, we require concentrated phosphoric acid along with steam in a high temperature of 300 degrees Celsius. Remember, the phosphoric acid should not be dilute, must be concentrated, so that the reaction can take place effectively. Again, if you check out this one, cyclohexanol is the product of reaction 2. Bond angle A is 109.5 degree, and they told you why bond angle. If you check out A and B, in case of B, there is oxygen atom, which means there are two lone pairs. In case of A, there are four bond pairs and no lone pairs. So since there are four bonding pairs, and we know that lone pairs repel more than bonding pairs, so due to the presence of two lone pairs around the oxygen atom, the repulsion automatically becomes greater, and as a result the bonds tend to lower down. So automatically the angle B is kind of less than angle A, which we expect it to be a little bit greater than angle B, considering there are four bonding pairs and no lone pairs. So the repulsion around the carbon atom in A right here is going to be less. So that is why we can say angle B is 104.5 degree, which kind of resembles to the water angle. In water also, in same case, we see that around oxygen atom the angle is 100.45 whenever there is the presence of two lone pairs around oxygen atom. Moving on, some ionic radies are shown. You can see the table is provided down here: Na plus, K plus, F minus, Cl minus. Now among the anions, this is the smaller anion. Among the cations, this is the smaller cation. Which compound has the strongest ionic bond? Now remember, all the time the strongest ionic bond is between the smallest ion. So if you can identify the smallest cation and the smallest anion, only then we can understand that between those two we can say that they have the strongest ionic bond. This is because it's pretty simple. The logic is pretty simple. If the ionic radius is pretty small, the force of attraction between them will be the strongest. So obviously the ionic bonding will also be the strongest. So A is the correct answer. Moving on, the bonding within an ammonium ion is formed by what? Now, bonding within an ammonium, we know that obviously covalent bond is there, and but there is another bond which is obviously dative covalent bond. There is one bond which is produced between hydrogen and ammonium. So obviously because nitrogen has lone pair of electron and Since nitrogen has one lone pair of electron, it can donate it with with a empty orbital of hydrogen in another uh, ammonium ion. So that is how basically an ammonium ion is basically produced by the presence of covalent bond between nitrogen and hydrogen, and the reactive covalent between nitrogen and hydrogen of another ammonium ion. So this basically tends to produce the molecule. Next, fluorine has one naturally occurring isotope with mass number 19. Now chlorine and fluorine basically react to form chlorine trifluoride. So they basically showed you this diagram down here. So again, dot and cross diagram is pretty simple. You tend to show the three bonding pairs, and since two lone pairs are there, because they are not used up during bonding process, so they'll be shown like this. State in terms of electrons. What is unusual about the dot and cross diagram you have drawn? Now the unusual thing is that there are 10 electrons in the outer shell of electron. If you see, so 1 2 3 4 5 6 7 8 9 10, two extra electrons are there. So that means there is an octet expansion. You can also talk about you can also write octet expansion instead of writing this as well. So this is the unusual thing, because we normally know that for full outer shell 8 electrons are required. This question is mainly about alkenes. A few drops of bromine water are added to separate tubes of propene and propene, and the mixtures are shaken. They told you to describe what is seen at the end of each experiment. Now, what happens in case of propene? Propene will obviously have a colorless solution. In case of propene, there will be an orange solution, because when you add bromine water, this is adding bromine water is basically called test of unsaturation, and we know due to the presence of double bond, the bromine water will get decolorized. So that is why it become colorless solution. But since there is no double bond, obviously bromine water's color will remain the same, which was orange. Again, for conditions, if you want to convert for this, we can clearly see alkene is being converted to alcohol. A little while back we saw, if you want to convert an alkene to alcohol, we require steam and concentrated HAPO4 in the presence of 300 degrees Celsius and 1 to 2 atm atmospheric pressure. If you want to convert an alkene to diol, we require a more stronger oxidizing agent, such as for example KMnO4 solution, potassium manganate 7, along with dilute hydrochloric acid. Always remember these reagents, because these are very important, like I said a little while back, for organic synthesis of unit 1. Now the question is about the phosphorus and some of its compounds. The atomic number of phosphorus is 15. You can see that. They told you to complete the electronic configuration of a phosphorus atom using the electrons in the box's notation. So you can clearly see this is 3s and this is 3p. We know we need to follow the Hund's rule and the Pauli excretion principle when we draw this. Now a little while back I explained this, that what happens is that since phosphorus, we can see clearly the three electrons are what, they're basically present in their unpaired state, but in sulfur one extra electron is there in its 3p subshell, making it in its paired state. So due to the presence of one extra electron in sulfur's electronic 3p subshell, what happens is that repulsion increases. So here stability decreases, while here the stability is higher. So if the stability is higher, if you want to remove an electron from its unpaired state, or from its stable state, obviously more energy will be required. So obviously ionization energy will be greater compared to sulfur, where due to the presence of repulsion, the stability decreases, and so less energy will be required to remove it. Again, phosphorus has a melting temperature of 44 degrees Celsius, and silicon has this. They said here that explain why the melting temperature of phosphorus is much lower than that of silicon. Now, the first things first is that silicon obviously has a giant covalent structure and phosphorus is a simple molecular structure. This basically sums it all, that phosphorus, due to its simple molecular structure, will have weak intermolecular forces between its molecules, while silicon atoms, not molecules, will have strong covalent bonds. Obviously covalent bonds are much more harder to break, so more heat energy will be required compared to the intermolecular forces between phosphorus molecules. That is why phosphorus has a lower temperature compared to silicon. Moving on, phosphorus 5 chloride exists as covalent molecules in the gaseous state. They're told to complete the table for a PCl5 molecule. For a PCl5, obviously there are 5 bonding pairs, we know that, and 0 lone pairs. So 5 bonding pairs and 0 lone pairs results to the production of a trigonal bipyramidal. And we can say in trigonal bipyramidal always there are 2 angles present in between between the bonds, which will be one will be 120 degrees and another will be 90 degrees. So something like this. So something like this, 120 degrees, and that will be a 90 degrees. So these are the two angles. Anyways, they said here that which sketch graph shows the trend in the first transition energy values going down group 1 in the periodic table. Now if you check, we know as we go down the group, the first transition energy decreases, so we can easily omit B from our option, and we can also omit C, considering that the ionization energy does not decrease in a, so in generally like this, because there are some anomalies present. So this leaves us A and D. Now what is happening down here is that we need to see is that what happens is that the first transition decreases, we know it down so good, but it starts more quickly at the start. So if you check it out down here in D, we can clearly see that the first transition energy, what with increasing atomic number, what happens is that the its value is very high, but as the atomic number increases, it tends to decrease very fast compared to this one. They basically did not, this graph does not actually explain the rate at which the ionization energy decreases with increasing atomic number across a, along a period, along a group. So that is why D won't be the answer. The answer will be A. All right. Moving on to the next part of our question, we can see the two stable isotopes of bromine have relative masses of 79 and 81. All right, so the next part of our question is that which is the correct pattern of peaks in the mass spectrum of the molecular bromine. Now if you check out all of the options down here, we know that there are many options, but the first, there are three combinations. So obviously, since there are three combinations, three molecular ion peaks will be there. So A and B is out of the equations. Among C and D, if we see that there is the abundance we saw a little while back, it was 1 is to 2 is to 1. That means the bromine 71, bromine 79, bromine 81, and then we have bromine 79, 79, and then we have bromine 81, bromine 81. So obviously bromine 79, bromine 81, if you add them up, you get about 160. This is 2 times in abundance compared to the other two. So obviously we can see this is more 2 times in abundance compared to the other two. D is the correct answer. Moving on, the bar chart shows the melting temperature of the first 20 elements. You can see the graph has been provided, and the bar chart basically tends to show the melting temperatures down here. Now what they told here is that, what they told here of giant covalent structures, uh, now what do they show here? You can see clearly they're basically showing giant covalent structures, right? And what is happening, increasing down each group. Now that is not correct. They're basically they do not, they're not there is no certain trend here which is showing that it is increasing down each group, or whether period 2, period 3. Among A and B, A will be the correct answer, because we can see that some of the metals, I mean, we cannot say that metals are always higher than non-metals, because some metals are there which have a lower energy, lower melting temperature compared to non-metals. So only option is giant covalent structure, because we can see carbon, silicon, all of them have giant covalent structures, and there we can see they're the highest in period 2 and period 3. So A will be the correct answer. The value of the molar volume of calculated P4 was lower than the student expected. Now give two reasons for the value being lower than expected. Uh, if I say so, there might be two, we have to give two logical reasons. So there might be a loss of gas before the bung is placed, so obviously this would result to a lower value, and some of the carbon dioxide may get dissolved in water, so this might be another reason basically why you can say that uh, you got the calculated value is lower. And the last things last, we can say the temperature of the lab was lower than the standard temperature, so obviously this would result to some of the gases being not to expand, and that is why the value would be lower, their molar volume would be lower, because we know that if temperature increases, the expansion of heat temperature is high. Moving on, if you talk about diamond, graphite, and graphite, all are forms of carbon. Now explain two ways in which the physical properties of diamond and graphite may differ. And you need to refer to their structure and bonding in your answer. So this is diamond and graphite, you know that. Now we know that diamond is hard. Alright, diamond is hard and graphite is soft. Alright, we know that diamond is hard and graphite is soft. Why is that the case? This is because we know diamond is a rigid lattice. It is comprised of only covalent bonds in the 3D structure. But if you talk about, graphite, they're in layers. there are weak forces between the layers. That means the layers can slide over each other if a force is being applied over them. So this is the reason why graphite is soft and diamond is hard. Moving on, state how the structure of graphene is related to the structure of graphite. Again, graphene has a single layer of graphite. This is how it is related to graphite. The graphene is basically, so graphite is a layered structure, also graphene is a layered structure, but it's just one layer basically. Moving on to the next part of our one, give a reason why the logarithm of the ionization energy rather than just the ionization energy is used to plot this graph. Now, sometimes the values of the ionization energies might be too large. That is why, in order to ensure that the numbers can be plotted easily on a smaller range, we tend to take logarithms because it becomes easier for us to make the graph much more simplified, and less less small numbers can be used. Explain what can be deduced from the graph about the electronic structure of nitrogen. Now if you do that, no whenever you check out the graph of the electronic structure of nitrogen, you will notice that there will be a big jump between fifth and sixth. Wherever you see big jumps, you will tend to notice that the electron being removed is from a new quantum shell. So there are two electrons that are harder to remove and they're closer to the nucleus, because as you keep on removing the electrons, the next electrons, the second or the third ionization energy will obviously be higher than the first one, because the second third electrons are being removed from inner shells which are much more closer to the nucleus. And on the other hand, there are five electrons that are easier to remove, and there will be some electrons obviously which are further away from the nucleus, so obviously less energy will be required, considering the force of attraction between the nucleus and the outermost shell will be less. So that is why the five electrons will be easier to be removed. And last one, I think we explained this a little while countlessly in 2 or 3 questions before, that why first ionization energy of oxygen is lower than of nitrogen. We just exactly write it down. We explained before. This is the answer. Last one is that 2019 January unit 1, they say that aluminum chloride exists as an ionic lattice in the solid state and as a covalent dimer. I told you in the gas phase, just above its boiling temperature. Now explain why aluminum chloride in solid state has significant covalent character. You need to remember one thing, that there is a relatively small electronegativity difference between aluminum and chlorine. So the electrons are partially shared. This is right. You need to talk about the electronegativity difference whenever this type of questions come. Whenever they talk about covalent character, you need to talk about the electronegativity difference. Lower the electronegativity difference, the greater the covalency character is. Or you can talk about in polarization form as well, where you can say that since aluminum has a smaller ionic radius, so obviously it will have an higher charge. That means the charge density will be higher, so it can easily more polarize chloride ions. This is the reason why aluminum chloride, due to the greater polarization happening, it has a significant covalent character. And that wraps up part 2. I hope this session helped you and you picked up some key insights along the way. If you found this useful, please like, drop your doubts in the comments, and share it with your study group. Don't forget to subscribe so you don't miss what's coming next. Stay focused, stay consistent, and let's crack this together. Bye bye.